drugs, or ideas, what you consume influences who you become. On the Mind and Matter podcast, we learn together from the best scientists and thinkers alive today about how your mind-body reacts to what you feed it. Before starting Mind and Matter, I spent 10 years in academia doing scientific research. I got a PhD in neuroscience where I focused on neuroendocrinology and the neurobiology of behavior, and before that, I specialized in molecular, developmental, and evolutionary genetics. I use my scientific background to help parse and translate the information that guests share on the podcast. In addition to the podcast, I write long-form written content inspired by the show where I integrate what I've learned across episodes. I also have a free weekly newsletter where I provide you with upcoming guests, share links, and provide commentary on scientific studies and research that I'm reading, and more. Visit mindandmatter.substack.com to find all of my content. The full version of this episode is available to paid subscribers at the Mind and Matter Substack at mindandmatter.substack.com. The full version is also freely available on my YouTube page. Just look up Mind and Matter or my name, Nick Jikomis, on YouTube, and you'll find the episode there. This is a partial version of the episode, and so it'll cut off partway through, but you'll still get a significant portion. So sign up to become a paid subscriber at Substack or visit my YouTube page to get the full episode. Hey everyone, I want to share with you a new AI-powered research tool I've been using to find scientific papers and learn from the literature. It's called Consensus. It is an AI-powered search tool built using large language models trained to help you find and understand the best science faster. Consensus helps you not only find individual papers, but its AI models will help you assess research quality and even synthesize insights across multiple papers for you. You can ask it general questions about any topic you might have, such as what are the known risks and benefits of a certain prescription drug? What do we know about how a certain food or nutrient affects the human body? Anything you can think of. Its Pro Analysis feature will actually provide you with a concise written summary of what the literature says, broken down point by point, highlighting the strength of the evidence across papers and providing you with individual studies ranked by the relevance and including additional information like citation rates, journal quality, and more. You can also save, cite, and share individual studies with a single click. Unlike other AI and search tools like ChatGPT, PubMed, or Google Scholar, Consensus uses over 20 custom large language models that are developed and trained for this specific purpose. The base Consensus product is totally free, but the premium product that you can subscribe to has better features and unlimited queries. And I highly recommend this if you are using outdated tools like PubMed or Google Scholar, or you just do your own research. For a limited time, you can use the code MINDMATTERSPECIAL, all one word, to get a free premium subscription for 1 year. That is a $150 value for free if you use the code MINDMATTERSPECIAL today. So click the link in the episode description or check my support page and give Consensus a try. Use the code MINDMATTERSPECIAL to unlock your free premium subscription today.
By just trying to build it, deconstruct it, change it, pop it, twist it, etc. And I've gained just a deeper appreciation for how core it is to just me personally, to like my loves, but also just how pervasive it is in society. I mean, the thing I would love to dig into today is, we published a paper in eLife about the relationship between biological metabolism and scent. Mm-hmm. And I haven't published anything on the topic since then, but I've done a great deal of work on the topic, and I've learned that relationship's actually much deeper than I appreciated. And there's other fields, it's super balkanized, but there's other fields that know way more than anybody that I've ever met in the world of olfactory neuroscience. Mm-hmm. They just know way more about the molecules. So there's this crazy thing that I discovered, which is if you go searching in the literature to learn about smell and use the word olfaction, reasonable technical term for smell, you learn everything that happens once a molecule hits a receptor and then goes into the signals go into the brain, and et cetera, and affects the rest of what the brain's responsible for, like behavior and language. But what about everything before that? Like, where'd the molecule come from? Mm-hmm. What made it? Yeah. Why is it there? Mm-hmm. What does it signal? All of that is actually completely ignored by the word olfaction. But there's a different word that picks it up called aroma. And it's a very subtle difference. Aroma and olfaction are sometimes used interchangeably, but in the scientific field, aroma is this catchword that pulls on this thread of flavor scientists, of people who do the metabolism of fermentation. It's like everybody who cares about the chemistry of how scents are created are tagged with the word aroma. And then
Hmm.
anybody who studies how the brain responds to these molecules are tagged with the word olfaction.
Hmm.
And it's so balkanized. There's such a clear dividing line. And look, I got a PhD in this stuff,
Right.
right? Like I went as deep as you could possibly go in olfaction, and the word aroma never once showed up in any context. And there's this whole other world of people that actually know what these molecules are and where they come from, and they have a ton to teach us. And obviously the olfaction folks have learned about how the brain processes these molecules, and they have a ton to teach the aroma folks. And it's like it's beyond strange that there's been a dividing line between the two.
Yeah, yeah. So I mean, what you're saying is, literally, if you look up one word versus the other, this
Yeah,
word will be plugged into a largely distinct part of the literature. It
yeah,
doesn't really talk to
completely.
the other one.
Completely distinct. And the the thing that I've come to realize sounds so stupid when you just say it, but scent is just molecules. Like what you're experiencing when you take that sip, if it's tea or if it's coffee,
Hmm.
all of the perceptual experience is mediated by just molecules. Easy to
Hmm.
say. But where do they come from? Because not all molecules have a smell that could have a smell.
Hmm.
And, a specific example is like the strawberry, maybe one of the closest studied fruits on the planet, second only to the tomato. There are maybe 10,000-ish molecules that are emitted by a strawberry, right?
Hmm.
Unique compounds that leave the confines of the strawberry flesh and get into the air. And maybe 1% of them have a smell, can be
Hmm.
detected
Hmm.
at reasonable values. But in order to perfectly recreate the smell of the strawberry, you need just 14.
Hmm.
And what's interesting about those 14 is every single one of them are metabolically downstream from nutrition.
Hmm.
So not one of those molecules is an accident with respect to why the strawberry matters to us evolutionarily. They're each just a few metabolic steps downstream from sugars, fats, or proteins, amino
Hmm.
acids. And not just any amino acids, essential amino acids, right? The ones we actually have to eat.
Yeah, yeah.
I think there's something, it's so obvious and like easy to state. It's like kind of duh, but it's, I just don't see people talking about this. And it's
Hmm.
become a very deep fascination of mine because it blurs the boundary between the sender and the receiver
Yeah,
of
yeah,
chemistry, you know?
yeah. And like when you think about aroma and you think about olfaction and why an animal why certain things would smell and why certain things wouldn't. You can think about it from, say, an animal's perspective. I might want to smell certain molecules in the strawberry because they're going to be signifiers of what's in there that my body needs. It's nutritional content. If I'm the strawberry, I might quote unquote want certain things to be smelled to attract, say, a pollinator or to repel another creature. And then, of course, there could just be things that are just byproducts. They might happen to smell or happen to not smell, but they're not really intended, scare quotes, by the sender or the receiver to be smelled. And so, how do you start to like think about things in that kind of ecological context in terms of
Yeah.
why our system evolved to pick up certain things?
Yeah. So fruits, flowers, and vegetables have had about a 500,000,000 years to collaborate and compete with their pollinators and their predators
Mm-hmm.
on the surface of the earth. And I just, when you look really close at these things, the boundary between the flower and the bee gets super blurry,
Mm-hmm.
right? It's pretty clear that, so take Lepidoptera, for instance, take caterpillars and the butterflies they turn into. There's some beautiful work from the 1970s that basically shows that caterpillars are speciated to feed on one kind of plant. And in a way, it looks like the caterpillar and the plant is one species because they're so tightly bound together.
Mm-hmm.
And it could be that, a plant evolved a new defense, and then randomly one day one caterpillar had some kind of chemical nullification of that defense or mechanical nullification if it's like spines and the caterpillar has some way of getting around the spines. But then you've created this syncytium of ostensibly two species that have to exist in lockstep with each other. If one dies out, the other's gone.
Hmm.
right?
Hmm.
Um, and that just makes the picture a little more complicated than what you learn in college biology,
Right. It's like
but it seems
it's
to
like
be
an
the case.
external mitochondria.
Yeah,
Yeah.
exactly. And like, why not? Like, what?
Yeah.
Like, life is super weird. Like, why can't that happen? And you notice that also for orchids and for some tree fruits, some orchard fruits. So there are orchids, I think there's an XKCD cartoon about this, but there are some orchids that look like they are imitating the sexual characteristics of insects that have long gone extinct.
Hmm.
And it's kind of like this museum of evolution or a thumbprint that has outlasted the thumb
Yeah.
in an interesting way. And you see this for some tree fruits that are too big and too tough for, let's say there's monkeys in a forest area that are eating fruits. There are fruits that exist in certain ecosystems that are too tough to be eaten by anything that exists today, but are basically a perfect match for megafauna that have gone extinct.
Hmm.
And for whatever reason, those trees can still they can procreate because the fruit falls to the ground, eventually rots. But they really look like they were evolved to be eaten when they were ripe by animals with bigger jaws that don't exist in that ecosystem
Yeah.
anymore.
Yeah.
And we're kind of, although a million years is a long time to us, that's kind of a blink of the eye. We're like, oh, the thing that they depended on has just disappeared, and maybe this thing will very soon too.
Hmm.
I think there's just something very beautiful about that idea to
Yeah.
me.
Yeah. You can see or smell or hear
Yeah,
echoes of the
yeah,
past in
yeah,
living organisms today.
exactly. Yeah,
Yeah. Going back to your what you mentioned about strawberries, which is interesting. You've got 10 on the order of 10,000 say molecules that are emitted by the strawberry that could be smelled. Only a subset are smelled by us, and it's
yeah,
presumably the subset that are smelled by one creature might not be the same as for the next creature. And
yeah,
you mentioned that the things that we can pick up on that are in the strawberry aroma, they are things that are metabolically relevant to us. And is that because so when I start to think about olfaction relative to other senses, where my mind starts to go is, well, when I think about the visual system or the auditory system or any other sensory system, right, the systems have evolved in order to be good at tuning in to certain features of that modality, like certain parts of the visual spectrum of light, and to ignore or not even be sensitive at all to other ones. So to what extent,
right.
like, when you mentioned that there's this very small set of things in the strawberry that we actually detect with our olfactory system, to what extent did we evolve the ability to detect just those things versus lose the ability to detect all the other things? To what extent is our olfactory system ignoring things versus just only being tuned to metabolically
Yeah,
relevant things?
yeah. First, just for folks to be able to follow along, there's a guy named Professor Klee, Klee, that devoted seems like his life, his professional life, to tomatoes and strawberries.
Mm-hmm.
And so there's a paper by Goff, Goff, and Klee that lays this out in a very convincing and succinct fashion about how few molecules matter for the core perceptual object that is the strawberry.
Mm-hmm.
I don't know where I'm borrowing the words from, but I'm kind of in piecing together literature. I kind of think of everything that is emitted by an object as the metabolic object, right? So there's the
Yep.
volatile metabolic object, everything that comes out that could possibly be detected.
Mm-hmm.
And then there's the molecules for which we have any ability to detect them at reasonable concentration. So
Mm-hmm.
in the metabolic object is a subset, which is the olfactory object. So things that could have a smell.
Yep.
And then inside of the olfactory object is this core skeleton of the things that we need to actually detect and that we're the most sensitive to. And if you mess with those molecules when you're reconstructing the smell, you no longer have a strawberry. You get something
Mm-hmm.
else. And in some of the literature that's called key food odorants, KFOs, there's a kind of a German group that's been studying this concept for some time. And it's usually a shockingly small number of molecules, like 5 to 40, that actually comprise the kind of essence of an object. And it's a controversial claim, right? I think there's still more work to be done. So why? Like, why is that funnel of why are we not sensitive to all 10,000 molecules? For RGB, which is the basis, across which we're sensing color and image, that is a span of just the spectrum of light that the sun emits, right?
Hmm.
So if you just plot like how much intensity in terms of like electromagnetism is coming from the sun, there's a big bump in what we call the visible spectrum, and RGB tiles that bump,
Hmm.
right? So like the prior over color is what the sun is shining on us. And in a sense, we have to ask what the prior over scent is,
Mm.
right? What molecules have been put into the air? And then of the molecules that are put into the air, which ones, if we detect them early, help us live longer?
Hmm.
And the molecules that are put in the air are overwhelmingly those made by life. Overwhelming,
Yep. Yep.
right? I need to go back to some of the references, but it's like I think 50 billion or it's 50 billion or trillion tons of biogenic VOCs in the air, right?
Hmm.
The anthropogenic VOCs, I think, are less than that. But, it's a lot of isoprene. It's a lot of CO2. It's a lot of things that are the off-gassing of life. Isoprene and CO2 being the terminal states of biological metabolism. You can't go past that. It's kind of the end of the sidewalk, as it were. That's an enormous soup to sift through. Like every inch of air contains, maybe megabytes or gigabytes of information about chemistry of the life that, was nearby or somehow contributed to that slice of air. We have to foveate chemically. So what do you choose to foveate on, right? The things that we need to detect are usually things we need to avoid
Hmm.
because they'll consume us, like fire or predators, or things that we need to consume ourselves, right? And there's a finite list of those things, right? We
Hmm.
need coenzymes, we need vitamins, we need lipids, we need carbohydrates, we need amino acids,
Hmm.
and a few other things. That's what matters for consumption. And then we need to procreate. We need to detect, conspecifics, folks that we can either have babies with, or that are our babies, or that are our friends.
Hmm.
And so that's not infinite in terms of the molecules that are out there. There's a finite set of molecules that kind of are signals to that. But what's interesting is every single one of those molecules is not volatile, right? So there's no nutrition that flies through the air. If
Mm.
that were true, we would be gaseous clouds, right? So ultimately, what we're trying to do is track down stuff that's leaking,
Yeah.
right? We're leaking chemistry all the time. There's a very, very thin slice of our metabolism that is catabolized into volatile downstream metabolic products.
Yeah.
That's what we're detecting with smell. So if you're going to engineer a system to try to basically invert metabolism and discover, okay, is there fat or protein or sugar nearby? You're going to want to focus in on the molecules that were directly produced somehow catabolically from those molecules and ignore the rest.
Right.
There's a great example that Arielle Johnson gave, and she wrote an awesome book called Flavorama. It just came out recently. And she has an example of two molecules that are pretty similar. And they both come from dye products. And dyes are really interesting because they often co-occur, like dyes in fruits, for instance, start to get produced when the fruit ripens. And that often has aroma changes, and often the aroma molecules are breakdown products of the dyes themselves.
Mhm. Which makes sense. It's signaling that the fruit is now ripe and probably
Exactly.
eatable. Yeah.
Exactly. So let's like somehow things have evolved to all be super tied together, which is biology's way, it seems. Now, some of those dyes can be turned into like vitamin A.
Hmm.
And some of those dyes can't be. They have no nutritional value, but they are dyes, right? They're
Hmm.
part of some kind of biologically necessary, kind of color structure. The molecules that are volatile, that are downstream of the dyes that can become a vitamin, are 250,000 times more intense to our nose
Hmm.
than pretty similar looking molecules that are downstream from dyes that aren't
Hmm.
molecules that can turn into nutrition.
So they're both dyes, probably very similar chemical structure, but one is relevant to us and one is not. And the sensitivity is just vastly different between the two.
Hugely different. And, I'm at this is kind of my nights and weekends science that I love to think about and do and read about and talk with people about. I have a lot of anecdata, man.
Hmm.
And I've done a lot of reading, but I don't have like a way to stitch it all together other than to share these really interesting factoids that
Hmm.
I can't stop thinking about.
Yeah. Yeah. But I mean, sometimes just talking about it is how the stitching starts to happen.
Feel like we're building a tapestry together.
Yeah, yeah. How much of our olfactory perception is how much of that map is plastic versus kind of hard coded from the beginning? So to think by analogy here, if I think about the auditory system and specifically language perception and acquisition in humans, we're all born with the capacity to hear, to detect
Right.
a relatively wide range of phonemes. Like a little newborn baby can hear all of the phonemes that are produced in all the languages in the world, but very quickly their brain learns how to tune into just the ones that are used in their native language,
Right.
and they become insensitive to other ones. So the insensitivity isn't baked in from the beginning; it's lost through learning. Do we understand if the olfactory system has that kind of plasticity?
Yeah. We may. I don't.
Mm,
There's a couple things there. One is there's a difference between what we smell and what we like. So
mm,
what we smell, just as you were mentioning, we can hear all the phonemes, just they may not take on meaning to us or association. For sure, it's the same in olfaction that like, and I think this is cross species, right? So when, for instance, we smell, this is a kind of a vivid example, but there's a flower that blooms every, I guess, many years. I forget if it's 7 or 4, but it's called the corpse flower. And it's for a good reason because when it blooms, it smells like a rotting corpse
hmm,
to us. And it is pollinated by the corpse beetle, which
hmm.
normally lays its eggs in corpses, which is just part of its life cycle. So that's an example that like there's probably one map of olfaction. And what we smell is probably shared across everything because I think we're basically smelling biological metabolism, right? We're
Yeah.
trying to infer the presence of certain kinds of nutrition or biological processes. Now, whether we like it super cultural, right? So Parmesan cheese and kimchi are divisive, right? And they're loved by some and disliked by others. It's learned for sure.
Hmm.
But then there's this other layer, which is like, all right, let's say I'm exposed to pine forests, but not tropical forests. Am I gonna not even recognize certain smells when I go to the tropical forest much
Hmm.
later on? I don't know, man.
Yeah.
There's a ton of bidirectional endocrine modulation in the bulb. And certainly when we're hungry, we kind of chemically foveate on certain scents over others. And there's a very close link to hunger and our internal kind of metabolic engine and
Hmm.
scent. And I wish I knew more about it, but that's about all I got.
Yeah. Yeah. But I want to talk about sort of the olfactory map and how the brain actually maps out olfaction. So, for those listening, obviously we have different senses. We can see, we can hear, we can touch. And in a nutshell, like a lot of the senses, somatosensory, the sense of touch, the auditory system, the visual system, those have been fairly well mapped out by
Yeah,
neuroscientists for a while now in terms of, we know how what the relationship is between how light hits our retina and how that's mapped out in visual cortex. And we can talk
yeah,
about the retinotopic map and all of the detail there. But that, we understood some time ago the logic by which the brain is encoding visual
right.
information. My understanding is that with olfaction, that understanding sort of lagged behind or it came later. It took us longer to figure out how the brain was actually encoding smells. And I know that
I
you've been
don't think we
connected.
know. I
We
don't
still
think we
don't
still
know.
know.
Yeah.
Yeah.
But do we know anything or is it still very mysterious?
So I think it's mysterious. So Bob Data, who's my PhD advisor, did some work in his postdoc advisor's lab, Richard Axel, and I think showed pretty convincingly that it looks like the projection from the bulb, which is like the first stop of sensory processing in the olfactory system, to the piriform cortex, which is like the smell cortex, just like what visual cortex is to seeing. So the projection from the bulb to the piriform looks random. And that's not what looks like it's happening in the visual cortex.
Hmm.
There's, as you
Hmm.
mentioned, this thing called retinotopy, which is like where things are on this surface of your visual cortex look like correspond to where things are in the visual field.
Hmm.
Nothing like that looks to be happening in piriform. Now, to me, there's an open question. Is it random or is it very, very high dimensional?
Mm.
And I don't think that we've addressed that. So, the work that we did, I don't know, we did the work like 5 years ago and published it, I think last year. Um, we were able to find a principal odor map that's about 300 dimensions that seems to be able to predict what a molecule will smell like better than a person can even describe it with respect to a panel of people. So we have this superhuman accuracy map of scent that's not three-dimensional. It's closer to 300. Nobody's gone and looked if there's a 300 dimensional topic map on the Puriform because that's really freaking hard.
Yeah.
Um, I think that's probably what's happening. Now, we would not know about retinotopy if we studied squirrels as opposed to cats or mice.
Mm.
Because squirrels don't have retinotopy. They
Hmm.
don't have pinwheel structures in their cortex. So, like, for whatever reason, squirrels can definitely see, but this topic organization that's real nice looking does not exist in that species, which seems just as smart as a mouse, maybe smarter. Um, what if that's happening for mice? That for whatever reason, our model species doesn't have topi, it doesn't, whatever the term is, doesn't have
Hmm.
a topic map, doesn't have a map-like organization on the surface of the piriform. The other thing to add a complication is it's super hard to study the piriform cortex,
Hmm.
right? I think there's
Just
like
because of
two
where it is.
where it is. It's under the jaw, right? So
Yeah.
the visual cortex, you pop, if you're doing the surgery, you just pop off the back of the skull. You know, with respect to other things you have to do, kind of neurosurgically, that's kind of easy. But taking off the jaw and going through a ton of vasculature to expose the piriform cortex, like I think it's just Stan Peshkovsky that can do that.
Yeah.
Maybe one other person, Dan Stetler. I forget who did that, a surgery equivalent surgery in the Axel lab. But like we're talking like pretty hardcore veterinary neurosurgery to do that exposure, and so it's just not studied.
Hmm.
And people put wires down in the brain, but like you need to expose the surface of the brain to do those kinds of experiments and really show it. And like, good luck finding people that have the hands to do that.
Yeah. Yeah. So how did you go about creating this 300-ish dimensional olfactory map?
Yeah. Pretty simple idea, which is if you can take a bunch of images and there's labels of what's in those images, and you can train a neural network to predict those labels, when you crack open the neural network in its embedding layer, which is the kind of layer that encapsulates all that's been learned about that data set for the purposes of making those predictions, the embedding contains a manifold of images. And it's this beautiful high dimensional compression of the space of things that one can see. And that's what a map is, right? And Jim DiCarlo's done a bunch of work correlating different levels of this processing with actual neural activity and the visual processing stream in mammals. And it looks like there's a correspondence. So there's something being learned that's sharing an algorithm, not an implementation, but an algorithm. We wanted to do the same with olfaction. And the trick is, okay, go get a bunch of molecules with structures that you can write down, just like you can on the whiteboard, you just draw the atoms and the bonds and the double bonds and all that stuff. And then associate those molecular structures with smell. So we were able to download, curate, in-license, purchase. I mean, we kind of by hook or by crook, we got 5,000 and I think 5,030 molecules in our database. And we associate it with the sense that a master perfumer would ascribe to those molecules. And that's the data set. And then you train a neural network, and you have to train a special kind of neural network that can deal with molecules as input. And that's called a graph neural network. And the big difference is most machine learning likes to work on rectangles, right? Like images are a grid.
Hmm.
Text is a very long, thin rectangle,
Hmm.
effectively. Sound is kind of the same thing. But molecules are not that, right? They can have a variable number of nodes. They can have weird connectivity. But fortunately, at Google Brain, in the years running up to when we decided to do this, some really brilliant people had figured out how to do that for the world of chemistry. And we just we drafted off of their brilliance and combined this idea of graph neural networks with the data that we had collected. And then there's a lot of art and craft that went into actually fusing those two together. But then we made predictions, and it turned out that that model could make state-of-the-art predictions better than anything else when you transfer learned it to basically any olfactory data set that we were able to get our hands on. So we trained it on expert human labels and then transfer learned it to other human data sets and got state-of-the-art. And that also turned out to transfer learn to other species. And that's kind of what got us excited about something that's deeper biologically there. And then, what you want to do is prove to yourself you have something real. And so what we did was we predicted the scent of almost a million molecules, and we kept those predictions secret. And we picked 400 of those molecules that were structurally really different from each other. They were structurally different from our training set. It's really critical to prove to yourself you have something that works, is to go kind of out of distribution.
Mm-hmm.
And then we predicted that they would smell different. And then what we did is we worked with Joel Mainland at Monell, and we trained a panel of people to reliably rate what things smell like. And the best you can do is the average of a panel, which is true for all data labeling. And our question was, okay, were our predictions worse than the worst person? Or were they in the middle of the pack? Or were they better than the average person
Mm-hmm.
in the panel? And the answer was they were better than the average person in the panel, almost better than two people combined.
Hmm.
And that told us, okay, we have something that's actually captured the relationship between a molecule structure and its odor and can do so at superhuman accuracy. I think there's something really here.
Mm-hmm.
And I think I've just been pulling on that thread since then.
Hmm. And so when we think about the relationship between the chemical structure of something that we can smell and what the perception is like, what people describe it as, what I think I've heard people say is that, I mean, one sort of naive idea would be, okay, well, if I've got two molecules and they're just sort of like one bond different, or they're very similar chemically, they'll probably smell similar. My understanding is that you can have two molecules that are very similar chemically, but they could smell completely different from each other, or one could smell and one doesn't. Is there some kind of orderly relationship between the chemistry and
Yeah.
yeah.
Yeah, it's biology, so no.
Yeah.
But it's true for drugs too.
Mm-hmm.
So in medicinal chemistry, this is called an activity cliff, where you have a great molecule that's an awesome drug, meaning it binds to some receptor or associates with some biological process, and you change one tiny little thing, and it becomes useless.
Yeah.
Or vice versa. You have something useless and you make a tiny tweak, and then it's a life-saving drug.
Yeah.
It's true for scent as well, where sometimes small changes don't affect the smell, and sometimes they can eliminate it or multiply its intensity by orders of magnitude,
Yeah.
or change its character from roses to rotten eggs. All of that is true. We tested that explicitly, and kind of that's, I think, the last paper and the last figure in the science paper. But being able to kind of straddle those activity cliffs is really important. Stress test of whether or not you've captured the microstructure of a map of symptom. Indeed, we were able to do that. Now, what's interesting is sometimes molecules that look totally different smell very similar. And what we were able to find, and this is a little bit in the science paper and in the eLife paper as well, is sometimes those two molecules may look different to a chemist or a computer,
Mm-hmm.
but they don't look that different to life.
Yeah.
Meaning, actually, those two molecules are one enzymatic step apart. So there's a protein machine which is actually designed to turn molecule A into molecule
Yeah.
B,
Yeah.
and they can look wildly different because enzymes can do some crazy
Yeah.
stuff.
And if
Like they,
instead of thinking of this as we're detecting the molecule in our nose, animals, maybe we should think about it as the animals are detecting indicators of some other biology that's out there that they
yes,
can then go investigate more closely.
yes. So you'd want that.
Yeah.
If that was true, you'd want that to be the case, and
Mm-hmm.
it seems to be the case. And it's been a source of frustration for a lot of modelers or machine learners in olfaction. But I think we should actually celebrate that because that's like the essence of what makes sense so powerful to us, I think.
Hmm. And so, it's easy to forget, how much history and how much work went into making certain technologies possible. So, like right now, we're on Zoom. I can see you. Obviously, we're on a video chat. I can hear you. We're talking. All of these things are pretty obvious, and we've known how to do that for a while now. This
Yep.
isn't cutting edge stuff, but I can't smell you. And the ability to do that sort of requires first, I think, having some kind of map or some kind of
Yeah.
understanding of the logic by which smell is actually encoded and decoded by a brain that can inform how we do similar things with physical technology that we build. And so, you're doing work now that is very much geared towards digitizing smell and taking that biological understanding of olfactory perception and using it to create new technologies. So, can you start to talk about how and why you wanted to do that?
Yeah. So the why is, I mean, there's the reason, the real reason, which is Because I think it's amazing. Because I think it would be so awesome if we could digitize this sense. It just seems like such a wonderful mountain to climb. Like I'm just excited by the challenge. Um, in terms of benefit to society, I don't think you have to look that much further than what dogs can do with their noses. They can detect disease, they can detect low blood sugar, COVID-19, um, harmful substances, and also what perfumers can do. They literally weave memories into our lives, right? Like the smell of a freshly cleaned home is an artistic creation. It has no intrinsic reality, right? The smell of fresh laundry was invented by someone. And I don't think that's a bad thing. I think that's a good thing. I think that's beautiful. In the same way that we have a favorite song that we dance to our partner with at our wedding, or a favorite song in high school that we sung out loud with the windows rolled down with our friends, right? Like these are creations that are hallmarks of our life. And I think that there's room for more beauty in the world, right? In the same way that like 100 years ago, before recorded audio, the world was probably didn't sound that great. And now, although there's like annoying music that's pumped in occasionally, like I think net, like we have more creativity, more beauty, and I'm grateful for it. And I just I see a world where that's true for scent as
Mhm.
well. And in order to do that, I think we have to automate an enormous amount of the toil that goes into creating scents and also detecting them. So ultimately, what I want is a device I can hold that can change the scent of a room and kind of change my mood. And I want that same or a different device to be able to detect if the air that I'm breathing is healthy and pure and clean, and to detect if the sense that I'm emitting from my sweat or my breath or whatnot indicates that I should make a change or if I should do more of the same, right? So should I take these vitamins? Should I avoid these foods? Should I work out harder today? Should I go see a doctor? Is there something really the matter? And look, in my lab behind me, I can answer all these questions and I can do all these things, but it's not small enough and cheap enough yet
Mhm.
for anybody to do it. And that's what I want to enable.
Mhm.
And I think that we have a long road to do that, and we have a plan to get there. And look, we've taken baby steps, right? So we kind of put this on social media, although we'd done it about 6 months ago, but we teleported the smell of a plum. So we
Mm.
took a plum, physical, fresh summer plum when they were fresh in the summer. We sliced it and we put it through our apparatus to take the chemical signal, turn it to a digital signal. We embedded it into our principal odor map, and then we reverse engineered it into a formula that we printed on a robot. And this is that plum.
Mm.
So in this is like the soul of 1,000 plums. I could smell this as much as I wanted, and it really does smell like snapping into a fresh plum.
Mhm.
We like made 100 vials of these to basically donate back to the science that we're doing. It's at osmostudios.ai. So it's like a cute art project, but really it's an indication that we've done it. Like we've actually digitized scent. It requires pretty big instruments right now, and we're working on making that cheaper, faster, smaller, and something that anybody can play with. So we've got some really cool stuff we're working on, and
Mhm.
that'll come out throughout the next year.
Mhm. So in theory, one place this could go is, at some point in the future, we could hop on a Zoom chat. I'm catching up with my friend Alex. I can see him. I can hear him. We're talking. I could say, Alex, what'd you do today? And you might say, well, I bought these flowers for my mom, and then I
Yep.
could smell them.
100%. Right. Or it's like, you know, hey, like this is my little baby girl
Yeah,
and she
yeah,
smells amazing. Like,
yeah,
like, just let's enjoy this like family moment together.
hmm,
Or like, oh, I've got a fire going, right? It's like
yeah,
warm,
yeah,
kind of comforting holiday vibes, like, come into my home virtually.
yeah, yeah.
Or just like, hey, what are we going to eat tonight, man? Like, let's go sample a bunch of different, cuisines on, some version of Grubhub that has the ability to digitally sample aromas. All that's going to come, right? Like, if you fast forward 100 years,
Hmm.
you can't imagine a world where that's not possible. Like,
Hmm.
it's just gonna be here. The question with Osmo is like, okay, do we have all the pieces to just fast forward that? Like, can
Yeah,
we make that happen in less than 100? I think in like 5.
yeah.
And it looks like the answer is yes.
Hmm.
And then, don't trust us until we don't believe us until we do it. But we're hard at work.
Yeah, and there's lots of different potential applications we can talk about. So feel free to sort of take the reins and move us in a different direction based on
Yeah,
what you guys are working on and making the most progress on now.
yeah,
But one area that I want to ask you about at least is sort of the medical and
yeah,
therapeutic side of scent and
yeah.
olfaction. So as you mentioned, we know that diseases can be smelled by dogs, for
Yes,
example. They can tell if you
yes.
have certain diseases. The
Yep,
the applications here are quite obvious. You could build a device that could do
yep,
non-invasive disease detection
yep,
very early on.
yep.
What do we know there and what are the possibilities?
Yeah. So there's a mountain of evidence, like a big haystack,
Mm-hmm.
that disease produces volatile chemicals that leave the boundary of our skin and can be detected. The haystack is made of a bunch of tiny studies that are all individually flawed, but they're flawed in their own separate ways. And so I really think that the evidence accumulates as opposed to collapses. There's been no one knockout study that really convinces me, you know, puts the nail in the coffin that says, yes, this disease has this scent and it is made of these molecules. I think there's a ton of anecdotes that are beautiful, like Mrs. Milne, who can smell Parkinson's disease. And I think that there's been subsequent studies running down what that chemical signal is. And like at every step of the way, yeah, like there's more work to be done to really nail that. The problem is that these studies are super expensive to run, right? So
Mm-hmm.
if you want to really get a chemical analysis of one scent in a way that you might if you were in an academic lab or even in an industrial kind of biotech context, thousands of dollars per data point. Really, because there's a lot of expert operator time. So where we focused our energy at Osmo is making running those kinds of experiments very cheap, and we've done that. They're cheap for us now. Because guess what? Like getting really good at fragrance, which is mostly the volatile kind of effluvia of fruits, flowers, and vegetables. Those are just the molecules that life produces. And it turns out that the molecules that mammals off gas, which are largely mediated by bacterial colonies that are eating our sweat and then kind of exhausting their own molecules, there's a ton of overlap there, right? Especially if you move from fragrance and also start to include flavor molecules, right? Like a lot of stuff in cheese, in meat, the volatile analysis of those foods are basically tantamount to the volatile analysis of us. So we've gotten really, really good at understanding the metabolic off-gassing of living things. And we've kind of set ourselves up a platform which is going to allow us to strike out into human health and wellness applications.
Mm-hmm.
The way I think about, I mean, stop me if you want to have a different conversation, but like we have a pretty firm view of how to tackle this now. And I've just studied the failures. I've studied what I consider to be some of the qualified successes. I think we need to start in the fragrance industry. And we need to get really good at designing scents that people love. And the very simple reason is that you can get paid for it today.
Mm-hmm.
And that's pretty prosaic, but like the money has to come from somewhere, man.
Yeah, which can be used to
And
pay for these other things that might take longer, be a bit more of a moonshot.
exactly. And like I view every single dollar that we make in Osmo as an opportunity to reinvest in the science.
Mm-hmm.
I'm here to do Osmo for the rest of my life. And what I want to do is create a virtuous cycle of revenue and of data that helps us strike out into even crazier domains in the future. And we just have to be super pragmatic that like, okay, like we're not default alive. Like we depend on venture money now, which I think is a better fit than government money for what we want to do. But like, no, I'd prefer to like make people's lives better and like build products for them. And so we're very focused on that. Every, ounce of improvement to our capabilities to design and, create fragrance makes the platform better, which makes all the other stuff that is kind of in the future easier.
Mm-hmm.
We still do incubate work. So, one other area that we've focused on is in supply chain. So this is weird, but if you buy a real pair of Air Jordans and then you buy a fake pair of Air Jordans and you smell them,
Hmm.
they smell different.
Like to a naive person, I can just tell there's a difference.
You, me, anybody,
Yeah.
they look the same. The counterfeits are super good. So if you go
Mm-hmm.
to Temu and you buy a fake pair of Air Jordans, they look exactly the freaking same as the real ones, but they're obviously not. They smell wildly different. It's just a super apparent. So we've actually deployed some of our scent sensor technology at StockX to sniff out fake shoes. So that's an example of like, okay, we're edging towards this new frontier, and we're doing it in a way which is self-fulfilling, kind of self-funding, so that we can, like, I care about going far, not necessarily speed running in an unsustainable way. So I want to make sure that we're moving towards our ultimate goal in a way which we can really keep up. And then that's like, so we've got fragrance as a frontier. Most of our focus is there. We've got security and supply chains, so just like kind of keeping supply chains, safe from counterfeits. We have some work there, small team. And then in human health and wellness, right now we have nobody, maybe like a half a person thinking about it. But we're going to grow that because I think we've over the last 2 years tackling this frontier, for at least for us in the way that we want to do it, has shifted from impossible to merely just very hard. And I think 2025 will start to really take a very close look at that.
And so talk a little bit more about what you guys are actually doing and what's possible in the fragrance industry. Full version of this episode is available to paid subscribers at the Mind and Matter Substack at mindandmatter.substack.com. The full version is also freely available on my YouTube page. Just look up Mind and Matter or my name, Nick Jikomis, on YouTube, and you'll find the episode there. This is a partial version of the episode, and so it'll cut off partway through, but you'll still get a significant portion. So sign up to become a paid subscriber at Substack or visit my YouTube page to get the full episode. Hey everyone, I want to share with you a new AI-powered research tool I've been using to find scientific papers and learn from the literature. It's called Consensus. It is an AI-powered search tool built using large language models trained to help you find and understand the best science faster. Consensus helps you not only find individual papers, but its AI models will help you assess research quality and even synthesize insights across multiple papers for you. You can ask it general questions about any topic you might have, such as what are the known risks and benefits of a certain prescription drug? What do we know about how a certain food or nutrient affects the human body? Anything you can think of. Its pro analysis feature will actually provide you with a concise written summary of what the literature says, broken down point by point, highlighting the strength of the evidence across papers and providing you with individual studies ranked by the relevance and including additional information like citation rates, journal quality, and more. You can also save, cite, and share individual studies with a single click. Unlike other AI and search tools like ChatGPT, PubMed, or Google Scholar, Consensus uses over 20 custom large language models that are developed and trained for this specific purpose. The base Consensus product is totally free, but the premium product that you can subscribe to has better features and unlimited queries. And I highly recommend this if you are using outdated tools like PubMed or Google Scholar, or you just do your own research. For a limited time, you can use the code MINDMATTERSPECIAL, all one word, to get a free premium subscription for 1 year. That is a $150 value for free if you use the code MINDMATTERSPECIAL today. So click the link in the episode description or check my support page and give Consensus a try. Use the code MINDMATTERSPECIAL to unlock your free premium subscription today. This episode is supported in part by Athletic Greens. Their main product, AG1, is a comprehensive and convenient daily nutrition product containing 75 vitamins, minerals, and whole food sourced ingredients with less than 1 gram of sugar per serving, no nasty chemicals or artificial anything. It's gluten and dairy free and compatible with paleo, vegan, vegetarian, and ketogenic diets. AG1 is a quick and convenient way to supplement your diet to help ensure your body is getting the nutrients it needs. It comes in powder form, and you can mix it in water and drink it, or you can put it into a smoothie or a shake or something like that. I mix it into water and drink it, and it's super convenient. If you go to athleticgreens.com/mindandmatter, Athletic Greens will give you a free 1-year supply of vitamin D and 5 free travel packs with your first purchase. Their vitamin D product comes in tincture form, so you just take 1 drop each day. A large fraction of the population is actually vitamin D deficient, especially in winter months when we get less sun exposure. And vitamin D is super important for the proper function of the immune system and for a variety of other things. So visit athleticgreens.com/mindandmatter or click the link in the episode description. You'll get a free 1-year supply of vitamin D with your first purchase.